Coming to part II, we will learn about subsets. Exercise. What does the diagram in figure 2 illustrate regarding the relationships between the sets of integers z and the sets of rational numbers q? Can we say each integer is a rational number? I'm going to analyze this problem. This is a Venn diagram serving two ellipses. The bigger one represents for a set of rational numbers. Cover small one represented for a set of integers. And I said in previous lessons, integers include negative, positive number, and zero. That's equal curly bracket from infinity, negative number like -4, -3, -2, -1, 0, positive number like 1, 2, 3, 4, and so on. And rational numbers include numbers in the form of a over p, with a and b are integers and p is not equal 0. A, p is not equal 0. So we see every integer can be written in form of a rational number with the denominator p is equal to 1 and numerator a is equal to that number. For example, we have integer 3 is equal 3 over 1. That is, the numerator is equal to that number. The denominator equal to 1. Okay. Another example, -2 equal -2 over 1. The numerator equal that number and the denominator is equal to 1. So set Z is covered by set Q is true. And the theory for this session: if all of the elements of set A are also the elements of set P, then set A is a subset of set P and is denoted as B. Interpreted as A is contained in B, A is contained in P, or we can read as A is a subset of set B, or B cover A, or B contains A. Instead of A is contained in B, we can write B contains A, and you see P contains A, P contains A. Okay. we use capital letter. Okay, capital letter. For example, set A include, you see, curly bracket was 1, 2, 3, and set B include curly bracket 1, 2, 3, 4. So A is a subset of B, because you see every elements of A is also in B. 1 is an element of set A, and 1 is an element of set B too. Similarly, 2 and 3. Okay, so we can call A is a subset of B. And if set A is not a subset of set B, then we write A is not a subset of set B. We can write A is not a subset of P. It's important. You have to distinguish the difference between two symbols. Okay, an element, this is an element, okay, and a subset. It's two simple. Okay, and we can read this denotation. A is a subset of B is equivalent for any x is an element of A, infer x is an element of P. Okay, continue. We have the following properties. A is a subset of A with any set A. B, if set A is a subset of set B and B is a subset of set C, then A is a subset of set C. Okay, you see, and this diagram in figure 4, you can see A is small set, B is a bigger set, and C is the biggest set. B contain A, C contain B, so C contains A. Okay, the part I equal sets. Consider two sets. Set A N is an element of natural numbers, so that N is a multiple of 4 and 6. Set B N is an element of natural numbers, so that N is the multiple of 12. Okay, so set A include 12, 24, 36, 48, etc. And set B equal curly bracket 12, 24, 36, 48, etc. So we consider 12 is an element of set A, and it is also an element of set B too. Likewise for 24, 36. Okay, so we infer set A is a subset of set B. Okay, now consider in the opposite directions. Set B is also a subset of set A. Okay, check the following conclusion. So you see, as I says, A E a subset of set B E true, and B E a subset of set A E true too. And this is our theory about this part. When A E contains in P and P E contains in A, we say set A E equal to set B denoted by A equal P. Therefore, set A equal to set B is the necessary and sufficient condition for any X, so that X is an element of set A if and only if X is an element of set B.